Okay, let's do office hours, problem solving, general camaraderie. Yeah, guys. Yeah. Yeah.
So my question is, for number 3, so let's say that I already have a regex. Could it say that I should construct a DFA for that regex? I know that I have to go to NFA and then DFA.
Yeah, you could go along that route, but you could just use the NFA for the part without the regexes that from, sorry, without brackets from before. If you did that, then just convert that to a DFA.
Okay.
Yeah.
And B is saying that using the DFA that I should construct an equivalent regular expression.
Yeah, so it's just doing the DFA or NFA to regex process, the GNFA method.
Oh, so I cannot, so it's good.
You can't just give the answer that you had above. Yeah.
I have to walk towards that answer.
Yeah, yeah.
I have to be able to get that answer.
Yeah. No. It's not going to be the same looking regular expression, but if you carry out to the computation, the regex language is the same.
Okay.
Yeah.
For that same problem, can I use that fancy like all non-transitions are go to the null?
Go to a state that go to a dead state. Yeah.
Yeah. Can I just write that?
You could. Yeah.
Okay.
Yeah.
Cool. Because Jake left
You can add one. Add trap state to finite automaton.
Okay. I'll try that.
Yeah.
Then I can just look
Yeah,
at it.
because I saw that too. So. Yeah. Other questions?
I guess, just as a question on that is acceptable to say all.
Yeah. If the DFA is very large, then yeah, do that. But I carried through the computation, and the DFA was quite small. So yeah, so I would avoid it if it's too small. But if you say it, it's not wrong. Yeah.
And similarly, just in a transition table, we just note that by the transition to go to was the empty set, right? That's the
well, it's just the name of a state.
Cool.
Yeah.
Okay.
Yeah. Mm-hmm. Yeah.
On the problem set, there's one that's like, this is regular, not regular. It's like
Yeah.
W and W 0 and 1.
Mm-hmm.
In my heart of hearts, I feel like this is not regular. It just helps me feel myself. And then I tried to pumpkin thing.
Well, if you write "I believe it in my soul," you might not get any points.
I tried doing it, right?
Well, if you can phrase it as another language that you've seen, that might be helpful. Or if you phrase it as a language that you know for sure is regular, then say what the language really is. So if I consider this guy,
Oh yeah, that guy's good to go. I get that.
okay?
But it's 0 1, not 1 0 1.
Do you think there's a reason I included both of those in the same problem? And something that's really helpful, read the book.
Gross. The whole book. That's it.
The whole book.
Start at the beginning and go on till you get to the end.
All 300 pages or so. Could you prove it's not regular? Other questions? I couldn't hear you.
Are we looking at specific problems or just
Oh.
basic questions?
Anything?
It also said, I tried to make it do all, and it said, just add one state, it's not too hard.
Yeah. There are some other error messages in JFlab like, well, we're done, go away. Yeah, question.
I have a question on number 5B. So that said that we should come up with a context-free grammar
Mm-hmm.
in Chomsky. So we have to have a CFG and then come back. So if I have a CFG that is different from each CFG, does that mean that I'm wrong? Or everybody has to come up?
No, there are many ways to approach the question in terms of what CFG you're going to make at the start, and the way that you process. So the rules, the 5 steps of converting the Chomsky normal form are, you have to do them in order, but the way that you approach them may not necessarily be the same. So you may get a different answer. That's totally fine. And you may start out with a different grammar. That'll definitely give you a different answer at the end, but that's not wrong.
So with my CFG, if I am able to produce a string that is in that language, then it's correct.
And not be able to not generate strings not in the language too. You want to accept exactly the strings in the language. Yeah. So just start out with a grammar. Make sure that your grammar at the start is correct, then apply the method. Yeah.
So I have a quick question pertaining to what we went over in class today.
Yeah.
That last part where you got in depth with the kinds of Turing machine, should we have a general idea on how to make those, or are those just kind of little tidbits?
What we're going to eventually see is that something called the Church-Turing Thesis, which is that any variant of, it's not that exactly, but any variant of Turing machines is equivalent to the standard definition of Turing machines. It's not exactly what it says, but that's a corollary of what it says.
But this is the build-up to kind of
Yeah.
Okay.
So next time we're going to prove that non-deterministic Turing machines don't give you any more power either. And then right after that, then we'll get into the Church-Turing Thesis, because it's like non-determinism is not going to give you more. Well, I doubt anything is. So, yeah.
Should we be able to solve problems like that of simulating more specific terms?
Very simple ones at most. So like the left reset and stay put, those are definitely good. Multi-tape and non-deterministic, when we do it, I doubt. Yeah, that would be way too much. Yeah.
I realized it wasn't that much of a trouble with. It was the WXW one, where X is spread equal 1, W is spread equal 1, and like length of it.
So,
That was the one.
yeah.
Sorry,
So this was the length at least one for both of them, right? Okay. Okay.
The issue was I tried doing the pumping on thing for it. I tried saying like WP, XWP, like that. I don't know.
Well, a W and X have to be strings in 0, 1.
Right.
Yeah.
But just like my issue was I thought anything they add at the beginning of it, you could just like have X
Well,
kind of.
if you make W at least P characters, could you touch that W at the end?
See, this is why I don't think I understand the pumping lemma. Because like, what am I trying to say? Like when I add more stuff in W, can't add
Well, you
just
can only add within the first P characters.
Would you want to pump X in that?
Well, if you make the W at the beginning P characters, you can only pump that part.
Right.
And so you can't touch the other W.
Right.
I'm giving a lot of hints.
Well, what am I trying to say? What's happening? Like if I had like
What is
0
happening?
to P, 1, 0 to P, right? And
Is it 1 then P zeros or 1 0 1 0 1 0 1 0 P times?
like 1, 1, all zeros.
Okay. So you're thinking this
I was tossing this out.
that string, right?
Oh, no, like 0, 1, 0.
So you're thinking this.
No, I don't know what I'm saying. Like, okay, anything I add at the beginning that's different, X.
Well, it depends on what string you pick.
I think you're right. Okay, so like I said, we like 0 to P. 1, 0 to P. So, like, yeah, that guy.
Okay.
Okay,
And
so do that.
then what's your X going to be?
I guess
X is some string in here, though. It has to be a fixed string.
Oh, I'm sorry. W, I shouldn't have said W. That's the whole string.
Okay, so
That's
so I'm guessing that
Yes.
it's like this.
Yes.
Okay. Okay.
So
So.
I have that.
Mhm.
And then I start adding more zeros.
Okay. So you add more zeros.
I get that like that W now doesn't match the other W, but can't X just like take those extra zeros and it's still in the language?
Correct. So how could you fix that?
I don't know. That's what I was struggling with.
Modify W.
What?
Put more on. Instead of 0 to P, put something else there too.
Oh,
That's not right.
There are many ways to solve it, but yeah. So it's certainly possible that this won't work. But so if you pump up, it may not necessarily work. If it's not up, what's another way that could work?
See, I think my issue is I feel like anything I change in zero, I can just like fix it with X.
Yeah.
Make W like make the beginning and end match.
Yep.
I don't know.
If you can force a certain substring to be in there, or some order, so if they start in so you have to think about it a little more. So remember that you don't have to pump up or down every single time. If it has a certain decomposition, then you can pump up, and sometimes you can push and pump down. It doesn't have to be the same for every single time.
What's pump down mean?
Set I equal to 0. Take the substring y out of the string.
Can I not do that because W has to have length
Well, so the naming on this is unfortunate. So let's pick not X. Let's pick V. Well, we want all decompositions of W, V, W into X, Y, Z with those three conditions. So so pumping down would be X, Y to the 0, Z. It's picking Y 0 times. Instead of X, Y squared Z, where you put Y twice. Yeah, so it's just pumping down, taking the Y out. So you're removing a character.
So if we have this now, the string that we'll be working with will it be 0, 0, 0,
Yeah. So WVW in this case would be 0 to the P, 1, 0 to the P. Yep. Other questions?
When we say choose W, it's not saying choose W, we just say choose WVW, right? Because that's the string now.
Yeah, so I should rename this to be like, say, S or something. But yeah, so I would choose S equal to this. Yeah. And if I just say WVW equals this, then that is actually ambiguous, because I could have V be 0, 1, 0, and the W part be 0 to the P minus 1. So you have to say what each of the pieces is, yeah, to be unambiguous with that. Other questions?
I guess I'm always just a little, since it's enough just to find one case that wouldn't work, to then say it's not regular, or that's, I guess,
No.
I was confused with all
Yeah,
decompositions?
you need to look at all decompositions according to those three rules, where x, y has length at most p, y has length at least 1. Right? You need to look at every decomposition.
Okay.
That's why making the first character be all the same is usually good, because you can only pump in that part anyway. And then you need to say for all decompositions, is there some value of I for which you get out of the language? So like if we happen to prove, for example, that x, y squared z gets you out of the language, then that will get a contradiction to what the pumping lemma says. So some value of I to get out.
And how are you fitting E into one of these? You mentioned E before.
E, I
The
don't know.
half song, the empty string.
I'm not in this question.
Not, it was in 4. It might be
It-
different.
I think you are meaning WVW, where are in 0, 1 star, and that's it. I think that was one. Yeah.
And
Mhm.
you put on, yeah, so that you could what goes
Yeah. Yeah. So what if I made W empty string? What does V range over? Everything.
So I was
Well,
just-
what is empty string concatenated with any possible string concatenated with the empty string? Mhm.
Well, I was just wondering, so star always includes that empty string. I just
Yeah.
like a brain part.
Oh, yeah, yeah.
So,
Yeah, 0 or more. Yes. Yeah.
In the homework, if we're building an NFA, is it better to have like a transition table that has every single combination, even if we're not using certain symbols, or would it be better just to write out the actual transitions?
Whichever is more convenient for you. As long as it's clear, that's fine. Yeah. Unless we tell you exactly what it is, which we won't. Just do whatever is clear and convenient. Yeah.
So this is more of a question about grading the homework.
Yeah.
People will have different grammars created for their
Yes.
problem 1.
Grammars?
Or like
Regexes.
yeah, regex.
Yeah. Mm-hmm.
And that would
course.
mean their number 2s and number 3s
Yep.
would also
It'll propagate. Yeah. So, in terms of like, I'll make sure that the grader works off of your solution.
okay.
Yeah. Yeah. If it happens to be different, then it's different, and then they'll just grade according to correctness of your original solution.
Okay.
Yeah.
So there's not like specific keyboard. Okay.
No. In fact, the NFA to regex conversion in question 3, if there are n states, there are n factorial different regexes, because you can rip out states in any order, potentially. So there's no way we would be able to handle all those. Other questions?
I have a question for RF. So, is it okay if I have a DFA that accepts W on its own, and then I change that to make it accept W ref, and then come back to return? Is that fine?
The problem is that going the other way may not take the same transitions as it went forward, right? Because once it reads it this way, it doesn't remember what it just read in order to go the other way.
If I make the NFA separate for the red and the
But it's the same input on. It's fed into the first machine, then it continues with the second. But it has no way of remembering what it just read. Because it has to be the exact same string but reversed.
right.
Yeah.
So it's wrong.
So that idea will definitely not work. So what may help is given a DFA, could you recognize all the strings that have length that are half in length of the original DFA? So if it happens to accept a string of length 8 in the DFA, the NFA that you'll make accepts strings of length 4. So that may help a little bit. So that's a standard exercise. Yeah.
So showing every step on 3B, how much of showing every step? Like, do I have to like do every single state that I'm removing?
You should.
Okay.
Yeah. That's why writing an algorithm is, making a computer program to do it for you is helpful.
Well, yeah, but would that show every single?
Yeah, you just have the program or whatever output the transitions, and then just display the table of the GNFAs in the middle.
Okay.
Yeah, but you can do it by hand. Either way is fine.
Yeah.
Other questions? You guys can't be out of questions already.
Review your Turing Machine practice problem.
Practice problem. Okay. I'm trying to think of a good example. Okay, yeah. This one's in the book, so you can cross-reference if I get it horribly wrong. But the language I'm concerned about is W#W, where W is an arbitrary string. I won't prove it, but this language is not context-free either. So I'll let you think about how can you prove that this is not context-free. But I want to make a Turing machine for it. So let's say that we're getting the input 0, 1, 1, £, 0, 1, 1. So is that string in this language? Yeah, because it's some string, £, some string. Well, what would be a Turing machine kind of idea in order to figure out that this input is correct? Or we should accept this input? Yeah, right. So I look at the first unmarked character on the left side, which happens to be 0 here. And since it has to be the same string on the right side, what better be on the right side? A 0. Okay, so let's try that. So I'm going to make a state like this. Well, I may see a 0 or a 1 on either side. Is that different logic? I think so. If I see a 0, I better mark a 0 on the right side. Right? I better mark a 0 on the right side. Same thing with 1. If I see a 1, I better mark a 1 on the right side. So I got to remember this in terms of states. I got to remember what I just saw on the left side in order to, when I eventually get on the right side, what thing to eventually cross off. So we're going to have two separate branches that will do similar things, but they are slightly different. So if I see a 0, I'm going to cross it off and move right. Let's say I go to Q1. Well, I want to go all the way over to the right side to the first unmarked character. Well, what will I see along the way there? Zeros or ones until I hit the £. So I'm going to skip past all of the zeros and ones. And then I hit the £. So I'm going to skip right past that guy because I'm going to only see exactly one of them. Then I go to Q2. Well, now I got to go to the first unmarked character. So what will I see potentially along the way? Will I see 0, 1s? The first unmarked character.
Unmarked meaning
The-
something that we haven't seen before? Or
Yeah, so the first unmarked character at the beginning, now I'm marking the same character over here. So what will I see before the potential 0? X's. Because I may have marked some things already, so I gotta go all the way past those to the first unmarked character. So I gotta zoom past all of those. But now I should see a 0. So I'm gonna mark that. And then once I mark that guy, what do I need to do? I need to go left until what point? The first half, but should I go into the X's over here? Well, I want to go to the first unmarked character on the left side. The first X. Good. So I need to move left here. Let's say this is Q3. So I gotta watch out, because if I say move left on 0, 1, £, or X, I might run into trouble because I might hit the left side.
So you have to do 0x and then transition to hash and then go until you get to
Well,
X.
I actually will only see X's until the £, right? So I'm gonna see only X's going left until I hit what? The £. Yep. So £, I better move left. And so now what will I see once I go past that £, until the first X? 0s or 1s. So I'm going to have X's, oh, not X's, sorry. 0s move left and 1s move left. And then I'll eventually hit an X, but where should I go? Back to Q0, because that's the state that I'm going to look at the first unmarked character. So I'm going to go all the way back here on X, but I'm going to move right this time. Because once I go all the way to this first X, then if I move right, now I'm going to be looking at the first unmarked character. So now we just have to implement the very similar behavior for 1. So if I see a 1, I got to remember that I've seen a 1. So, but the behavior is identical otherwise. So here, I'm going to zoom past all the 0s and 1s on the left half, and then go past the £, and then go past all the already marked things. And then now the important transition where I hopefully see a 1, and then I cross it out. So it's identical other than the 2 starting transitions and the 2 ending transitions on these 2 branches.
We couldn't reuse like go from Q5 to Q2.
No, because I need to remember that I've seen a 1. Yeah. Because if I combine those, that just means that at that point I'm recognizing that the 2 parts have the same length, not necessarily the same word. Well, suppose I marked everything correctly on both sides. What will I see when I move left and then move right? When I come back to Q0?
After an entire iteration.
Yeah, entire iteration. The entire left half is marked with X's. What will I see now? A. what? On the left half, the entire left half is marked with X's, and I move right, and I hit a pound sign. Good. So we got to, well, if I hit a pound sign, what better the right half be entirely? X's. If I see a 0 or 1 over there, it's not the right input. So let's handle that. So I'm going to have pound sign, move right. So I want to now check the second half of the input. So I'm just going to go past all the X's. And then what better I see after all that? The blank symbol. Good. So if I see a blank symbol and move right, what should I say to that input? Accept it. Good. Okay. So the idea was, in order to design this machine, remember what symbol that you just read, and then go all the way and mark the corresponding symbol on the other side, mark it, then go back. And then the stopping condition is when we hit that pound sign in the middle, when we want to do another iteration, and at that point, we know that it must be of the form W pound sign W if the entire right side was marked. But are all transitions here? No. So I better say all other transitions go to Q reject and move right.
I've noticed that like a lot of times in class we build on like algorithmic practices to make it just thoughtless as much as it can be.
Yep.
Why? Is there a reason why we don't just immediately, the same thing that the way we did with PDAs, like put a special character at the beginning, why we don't just immediately do that with our Turing machine?
Because in PDAs, we had a separate entity. We had the input tape and a stack separately, where the Turing machine is the same thing. There's only one thing, and we're overwriting the input that's already there. Yeah, so the input's destroyed in a Turing machine potentially, but in a PDA is always kept, preserved. And in a PDA, you can't go back across the input and change it, whereas a Turing machine can.
So is it more just like because of a practical realization? Because if we're not worried about time,
Mm-hmm.
then can't we essentially preserve all of our input, and it's just essentially adding another linear step to it?
Mm-hmm. Yeah, you certainly can do that. You can copy the input over with the delimiter and run on that second part. Actually, in one of the theorems in the NP completeness stuff, we will use that idea, preserving the input. Yeah.
Why does it say for all of the transitions that it also moves right? Like once you're in
Yeah.
can't go with
Because it may be possible that I'm in the leftmost cell. Like in the instance pound sign 1, then, I don't know.
But why do you have to do a transition at all?
Well, in order to go to Q reject, I need to do a transition to get there. And I need to move left or right, no matter what.
Oh, you always have to?
Always move left or right in the standard Turing machine model, yes. Yeah, so I need to say what the transitions do, and I'm technically, no. Actually, if I have the input just 1, then at the beginning, there's no transition on, oh no, there is a transition on 1. Maybe if it was given just X, there's no transition on X. And if I said move left, then I'm toast. So, yeah, it's never wrong to say move right. But it may be wrong if I say move left. Yeah, but I do need to go to Q reject on the other transitions not here. Yeah.
So, the difference between decidable and recognizable,
Mm-hmm.
since we built this for this language, it has to be recognizable.
Yeah, for sure. Has to be.
Or it's only decidable if at the end of input it's either in the state Q accept or Q reject.
Well, you have to say what the in the end is. It means that every input takes a finite amount of transitions.
So for
All inputs. So is this language decidable? Or is this Turing machine a decider? Yeah, because what do? We mark off 2 characters of the input, and the input's finite, so therefore we only have a finite number of steps. So this language is decidable.
Are there
And therefore also recognizable. Yeah. What was there?
Or are there strings of input length?
No, because strings are defined to have finite. Yeah. I mean, there's something called omega automata, which deal with infinite length strings. Yeah. And that's interesting, but we aren't talking about that. Yeah. Yeah. So a Turing machine is a decider if, for all inputs, it stops after a finite amount of time. So it doesn't run forever on any input at all. And the language is decidable if there's some Turing machine with that language. Sorry, a Turing machine decider with that language. What's that? I didn't hear.
Is that like, recognizable? Yeah, I mean, I think what you said is the definition for recognizable.
No, recognizable was for the strings in the language, it has to halt. For decidable, every string halts, even the ones not in the language. Yeah, so recognizable for the string that's not in the language is not required to halt on. It can, but it doesn't have to. Okay? Stops. Stops and either accepts or rejects.
Usually for the recognizable, the string have to be stopped as a, like, accepting.
Yeah, the strings in the language, only in the language, have to stop and accept, have to halt and accept.
That's the recognizable.
Yeah, that's the only requirement for recognizable. But if you want to also say the strings not in the language also halt and reject, that's decidable as well.
Oh, okay.
Okay? Other questions? What's that?
I mean,
I didn't.
we are building up a lot of things here, and there's a lot of relationships. I think that if you miss something in the middle, like you'll flounder later. So are there good like references that kind of, or I mean, I'm trying to build my own, but that you would recommend
Reading ahead.
reading it.
Reading before lecture. That's the thing I said the first day. So.
Oh, well, meaning I was thinking more of like the relationships between building up in like, you know, all regular languages are,
Yeah.
you know.
Yeah, so I did that once today. I'm going to do it once we talk about languages that are recognizable but not decidable. So we can build this hierarchy up. I will talk about that, but is there like a specific example? Or?
No, I just think like the first thing, I missed that all finite, anything finite is regular, and
Yeah.
that totally I screwed the food there. But I'm just saying, like, I don't want to miss that again.
Yeah. So come to class is a good one.
Well, I did.
Not you specifically.
I got it.
Yeah. I mean, yeah, there are quite a few things. I'm trying to think of a good
I'm not saying
Yeah.
that. I don't know. I'm sure something exists, and I would like to. I'm doing it myself. Yeah,
just thinking about like what the types of languages are. That's the important thing. Like for the finite example, it's just knowing that regular languages are not closed under infinite unions, because what you can do is for any infinite non-regular language, just make a little language for each of the individual strings, and each individual string is regular, and so their infinite union is the non-regular language. But a finite number of unions always is regular. Yeah, so it's just, yeah, it's little things like that. Playing around with the definitions, like do we really need this condition, or could we get away without not having it? What if we had a finite language? Could it be regular, or could it be non-regular? Is there a context-free language that's not regular? Is there a context-free but not regular language whose complement is also context-free but not regular? Because even though we don't have closure under complement for context-free languages, that doesn't prohibit a context-free language from having complement who's also context-free. So it's just playing with the definitions a little bit. I think is a good trait to have in theoretical computer science in general.
Okay.
Yeah. Yeah.
Along those lines, like, we know that regular languages are context-free languages, and we know that decidable languages
Are recognizable.
So how do we connect those two things together?
So we'll talk about, when we talk about encodings, which we'll talk about probably tomorrow, Friday, we'll talk about how can you decide whether or not a grammar can accept a string. And there are many algorithms out there, but one we'll talk about is convert it to CNF, and then look at every derivation of length 2n minus 1. Because the derivation length of a string of length n is always 2n minus 1. So just enumerate all of them, and then just see if any of them result in W in the input. That takes a finite amount of time because there are only finitely many derivations of that length. And so therefore it's a decider. So therefore all context-free languages are decidable because they have a CFG, and then testing whether a certain string is in that language is a decidable problem. So regular languages are context-free languages are decidable or recognizable. So luckily, we only have a uniform hierarchy here. So regular is a strict subset of context-free, strict subset of decidable, strict subset of recognizable. Yeah. So I have in the syllabus, I'll talk about complexity theory, and then that's full of non-uniform hierarchies and stuff. It's really weird stuff, but it's pretty cool. So hopefully I get to talk.
You stated a few times that we're kind of ahead in terms of where we're at the schedule.
Yep.
What happens at the point when we finish ahead of schedule? Like, where do we go from there?
I'll talk about NP completeness, p-space completeness, and complexity theory. So some really cool stuff like so the motivation behind that is a lot of problems in AI and among other fields are what are called p-space complete, and by that notion we don't know whether or not they have an efficient algorithm or not. So that's why there are, so like an example problem is, so here's one that's what is called exponential time complete. And it's generalized chess. So given a configuration of the chessboard, of an n by n chessboard, is there a strategy for player one to win?
Like from any point in time in the game?
You're given the configuration at a specific moment. Is there a way for the player one to win? And that's what is called exponential time complete. And one theorem I doubt will prove is called the time hierarchy theorem, which says that if you give any extra power in terms of the amount of time it takes to solve the problem, then you get more languages, strictly more languages. And so therefore you can show that this problem does not have a polynomial time algorithm. And so therefore there's no efficient algorithm to solve chess in general.
So once you go beyond the one bound, then you're...
Yeah. And so that's why artificial intelligence is so important in trying to approximate hard solutions to really hard problems. Another one I hope will prove is Super Mario Brothers, is NP complete. So the problem of you're given this Super Mario level, and you want to determine whether there's a way for Mario to reach the goal or not. And that problem is NP complete, and since we believe that P is not equal to NP, there appears to be no polynomial time algorithm to solve Super Mario Brothers. So that's why certain problems of that nature are really hard. So there's this great class by Eric Demain, who works at MIT, called Algorithmic Lower Bounds, Fun with Computational Hardness, and they look at Donkey Kong Country, Zelda, Minesweeper, Super Mario Brothers, all these problems, and prove really hard results about them. So
We say Minesweeper.
yeah, yeah, it depends on how you phrase the problem.
Okay,
Yeah.
that's...
Yeah, I was thinking of having a class this fall, but I couldn't get approval for it. But it's a class with video lectures and everything. It's really cool. But in terms of the material, it's in chapters 7, 8, and 9 of the Sipser book. Yeah, and actually 10 too, but yeah.
So the extra content that we go over, once we hit like the end point, and
Yeah.
start doing the extra stuff, will the extra stuff be on the final exam, or would that just be?
TA, ask me anything except what's on the test. It's a shirt I have. I should have that be testable material, but we'll see how things progress.
As far as preparedness,
Yeah.
if the extra content is something we should be worrying about.
Yeah, because being able to reason about problems that involve P versus NP completeness, I think that's an important skill to have. And I should make it testable because P versus NP completeness is the least understood topic in computer science. Like, I got sick of correcting people on the internet because people got it so wrong. So
you're fighting the power.
no, I got sick of doing it. So I'm gonna have an actual class for it. So, but I think it's really cool stuff. So
you will let us know.
Yeah, I'll let you know.
So you're basically going a little bit deeper into things versus what was going on in Colbert's class last semester.
No, not deeper, broader.
Broader?
Yeah.
Okay.
More topics. Yeah.
More
Yeah. 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 Hopefully you all don't maul me by the end of this class. Yeah.
So for the Turing machine, the basics that we're doing, we always have the blank symbol at the end of all the strings that we can
Yes. Yeah. So after the input is an infinite sequence of blanks after. Yes.
We don't have to have it before.
No, you can't, because the input alphabet doesn't have the blank character in it, and the input's always left justified on the tape.
This is the example that we did in class. We replace 1, 0 with.
Yeah, you can write it after, but right at the very start, the input's left justified. I could put blanks everywhere if I wanted to, but I don't. Sorry, I don't have to.
But it's always in the back.
Yes, yes, to the right. Yeah.
So the fact that there could be blanks anywhere, but that ends up just being covered in all other transitions go to.
Yeah, if it doesn't happen to have it, then you say all of the transitions go to Q reject, then it'll go to Q reject. If it encounters a blank, yeah.
And that would still solve our having a blank. In the example we did earlier, a blank in the middle of that would have destroyed that string as being able to get to the system.
but the initial input doesn't have it because it's not in the input alphabet.
Oh, okay.
Yeah, so that avoids the ambiguity problem of where the input actually is and what it actually is. So, yeah.
Okay.
Other questions?
said that being a decider, it handles all strings.
Yes.
That would include symbols not included in the input alphabet?
No. So all strings over the input alphabet. Yes. Yeah, it's over the input alphabet. And it halts on every one of those. Other questions?
So wait, essentially, anything that just halts would be a decider or TM or no?
If it halts on every input, then it's a decider.
Oh, okay, so it can't just halt on one.
No, no. Yeah, it has to halt on all inputs. Yeah.
Okay.
Yeah.
So I guess my question would be, is there like a small example of a language that you can show us that's recognizable but not decidable?
Not with the current tools that we have, because I haven't proved that it's not decidable yet. But because we haven't talked about encodings, and that's we got to get into encodings first. Yeah. Don't worry, we will. Other questions? I can let you guys go 5 minutes early, unless there are other questions. All right, I'll see you on Friday.